are some of my highest water rocket flights to date, and they're honestly not that high. The highest are only to around 200 feet. But how do you make a water rocket fly higher? There are many ways, but a very good one is to increase the amount of fuel. But how do you do that? The first thing you might think of is to make it a bigger diameter. The problem is that this decreases the amount of pressure the rocket can hold. Increasing pressure also increases altitude, and this is much harder on a larger diameter pressure chamber. So, what if we increase the length? This works to a point, but also has some pretty big drawbacks. A long, thin rocket is very difficult to keep rigid, which can cause it to bend or fold, which is not great, and it also makes it hard to add a second stage. A long rocket is also difficult to transport and may also require a longer launch rail. Something a lot of people do, and what I decided to do, was use multiple small diameter pressure chambers clustered together, which allows for small chambers that can hold high pressures without having a super long rocket. This is Psi, my cluster water rocket. It is made up of these 3 booster segments you can see here, and it was heavily inspired by Air Command water rockets, Acceleron 5, and Project Horizon boosters. You'll notice that this rocket has a large space in the middle, and this is where the sustainer would sit. You can see that here. This is another very big advantage of this type of rocket. You can see the booster segments support the sustainer, which really helps prevent it from folding. The core of this design is the central bracket here, which takes the load from the thrust rings and transfers it to the release mechanism on the ground, which is my standard release head. The release head is attached to this pad, which supplies air to all 3 booster segments. We have 1 fin on each booster segment, which gives us 3 fins total, and at the top you can see this hexagon here, which holds everything in alignment. This isn't super important on this rocket, but on a longer rocket it will really help with the rigidity of the booster and keep things aligned. Finally, here we have the recovery system, which holds 2 parachutes. They will both be deployed out of only 1 recovery system since it has plenty of room and it makes it a lot easier to build. Once I finished with the design, I started 3D printing parts. Then I printed some more parts, and then some more parts. There was a lot of 3D printing. Because this rocket has 3 segments, almost every part has to be printed at least 3 times, meaning this rocket has about 40 printed parts, most of which took over an hour to print. Once the parts were printed, I started to put them together. The first thing I did was glue some fiberglass plates to the central PVC tube using an alignment jig. Once those joints were reinforced with 5-minute epoxy fillets, I added the thrust pads. These go up against the booster segments and sit against the thrust rings and are also filleted with epoxy. They are zip tied to each booster segment to hold them in place against the thrust ring. After the bracket was complete, I glued the thrust rings to the booster segments using PL Premium, which sticks well to soft drink bottles. With all these steps complete, I was able to do the ground test. Okay, so we've got the rocket set up for a ground test. We're just going to bring it up to pressure to make sure nothing breaks. In case something does break, we have all these towels that we're going to put over the top to keep it from going too far. That it?
Yep.
How fast is it leaking?
I think it's just like figuring out the pressure, like.
Yeah, it might be leaking a little. It's leaking a little bit, but it's plenty. It's good enough for a launch. With the ground test successfully completed, I was able to continue with the build. The next step was to assemble the top ring, which included cutting out parts from corrugated plastic and bolting it together with 3D printed parts. The fins bolt onto plates that sit against the same thrust rings as the central bracket. The recovery system deploys the parachute out the side and screws onto the top of one of the booster segments and is controlled by a servo and RC receiver. Once the fins and recovery system were installed, I packed up all my launch supplies and headed out to the launch site. Okay, we have the rocket set up on the pad here out at the launch site, the park. It's about ready to fly, so we're going to give it a test. I really hope it works. Basically everything is out of alignment. It's super janky, but it'll probably work. Shoot.
Oh no! Release, release! Oh no!
So, that launch was a little less than ideal. But what happened? The direct cause of the failure is pretty simple. This parachute mechanism has this ejection plate with rubber bands, and either the parachute got jammed in there or they just weren't powerful enough to push the parachutes out. You can see in the flight footage that this door here did not come off the parachute bay, which tells me that the parachutes didn't even exit the parachute bay and stayed stuck inside the whole time. The crash wasn't the only failure of the day, however. We forgot a couple of flight critical components. So this parachute bay has a hole in the back that allows air to be supplied to a second stage. When flying in a single stage configuration, this is plugged with a simple bolt with a plastic washer. This is really simple and easy to do, but I completely forgot to bring the bolt to the launch site. So we had to drive home and pick it up. We also completely forgot this adapter that adapts our electric bicycle pump to our standard quick disconnect that connects to all of our other launch hoses. So we had to drive home separately to pick that up as well. Although the parachute failure and the forgetting stuff failure seem pretty unrelated, I think they might be fairly connected. They boil down to two causes: time and overconfidence. The time one was that I was kind of rushing to get this rocket launched by the end of the weekend, and so I skipped important stuff like doing a rehearsal to make sure I had everything or testing the parachute ejection mechanism. I also rushed the avionics build, and that may have caused the servo to not even deploy, causing the door to stay attached. I also made some last minute changes to the parachute system that may have contributed to the failure. The old ejection plate was thick because we had such a small parachute, but for two parachutes I needed a thin one, and I didn't want to wait to print one, so I just cut this one in half, and that may have been part of the problem. I also felt overconfident in both my parachute system and my checklists for what to bring, which meant that I didn't run ground checks on the parachute system or run a rehearsal to make sure I had everything because I felt pretty confident that the parachute system would work. I've tested it in flight a lot, and I felt pretty confident that I had everything because I have pretty thorough checklists. But I relied on my checklists a little too much and forgot important stuff. Although this was not perfect, there were some pretty good successes. It released cleanly from the pad. I was pretty worried it would get jammed. The fit is pretty tight, and it was hard to get on the pad, so I was worried it wouldn't have enough force to release. I did notice something that slightly worried me. The thrust plumes from the booster segments were not very well aligned, which either means that I did a bad job aligning them during the build, which would be fine, or more worryingly that they were flexing during launch, and that would not be very good. You can see the rocket arc over at launch, but this was very expected. We only had this parachute bay on one booster segment, so the center of mass was really offset, meaning it arced over pretty bad. I was overall, though, very happy with the flight, even though it was not the most successful. So, what's next? At some point, I will refly this rocket with the second stage in place, but first I have to figure out the recovery system and make sure it is easy to get onto the pad. Another upcoming project is a test campaign to create better fiberglass pressure chambers. This will involve creating multiple test pressure chambers and testing them to failure, which is usually quite exciting. There'll be lots of explosions. So that's all for today. Please like and subscribe if you enjoyed the video, and I will see you next time.